In 1893, Charles Steinmetz gave a lecture at the International Electrical Congress in Chicago. There he showed that calculations with alternating currents and voltages could be simplified using complex numbers. We will follow in Steinmetz's footsteps and see how AC voltages and currents can be described by rotating arrows. In doing so, we will see how the addition of voltages and the relationship between voltage and current motivates two geometric operations with arrows. Then we will see how these operations can be constructed with compass and straightedge, and what properties they have. Finally, we will learn about the imaginary unit and the usual Cartesian representation of complex numbers. One of the most common electrical components is a resistor with resistance R. If a current I flows through it, there is also a voltage VR across the resistor. With proper direct current, neither the current nor the voltage change direction or even strength. With alternating current, however, the current and the voltage change periodically direction and strength, usually sinusoidally. In the case of a resistor, this change happens simultaneously for current and voltage. If we plot the voltage against time t, we get a nice sinusoidal function, which repeats itself one oscillation after the other. The time duration for one oscillation is called the period T and is measured, for example, from one maximum to the next. Its reciprocal, the frequency, tells us how many oscillations take place per second. If the voltage changes faster, the period becomes shorter, and if VR changes slower, the period becomes longer. Thus a change in period scales our sinusoid along the time axis. The maximum deviation from zero voltage is called the amplitude and is usually denoted with a little head above the symbol. Changing the amplitude scales the sinusoid along the voltage axis. Now, there's something very interesting about sinusoids. We can imagine that they are generated by an arrow rotating counterclockwise with constant speed. At each instant, the voltage value is the vertical distance of the arrowhead above or below the horizontal axis. If we assume that the rotation started an infinitely long time ago and continues forever, this rotating arrow completely generates our sinusoid. Within one period, the arrow must make one complete revolution. It must therefore rotate with an angular speed or angular frequency, omega equal to the full angle tau divided by the period T. Rotating arrows are fun, but we don't really have to rotate them, just imagining it is enough. So we can go to any fixed point in time, let's say 0. If we imagine the rotation, this fixed arrow describes our sinusoid completely. For example, if we change the arrow's length, we also change the amplitude of the sinusoid. Until now, the arrow happened to point horizontally to the right at time 0. But what if this is not the case? It could be that we started our clock a little too early, before the arrow was yet horizontal. Then it takes a little while for the voltage to become 0, which moves the whole sinusoid backwards in time. It could also be that we started our clock too late, after the arrow was already horizontal. This shifts the whole sinusoid forward in time. So our fixed arrow at time 0 has a length equal to the amplitude and an angle phi r called phase measured from the horizontal axis. Such an arrow is called a phase vector, or phasor for short. Its two properties can be combined in the phasor notation by writing the phase in a small angle symbol. We can shorten this even further if we just underline the amplitude to remind us that there is also a phase. If we have only one phasor, its phase is physically not very important. It only changes the numbering of time. But as we will see, the phase difference between two phasors does have a physical meaning. Electrical circuits get a bit more interesting if we connect two electrical components in series, for example a resistor with resistance R and a capacitor with capacitance C. Since they are connected in series, the same current I flows through the resistor and the capacitor at any time. As already mentioned, the current I and the voltage VR across the resistor change simultaneously. They are in phase. However, this cannot be the case for the voltage across the capacitor. Why? As long as the current flows to the right, the charge on the left plate of the capacitor increases and the charge on the right plate decreases. This happens as long as the current doesn't change direction, even if its strength is already decreasing. Thus, the voltage we see across the capacitor is maximum exactly at the moment when the current becomes zero and changes its direction. As soon as the current flows to the left, the charge on the left capacitor plate decreases and increases on the right plate, causing the voltage we see to decrease and eventually change direction. Then everything happens again with reversed polarity before the complete cycle repeats. Thus, the voltage we see has the same period as the current I and the voltage VR, but always lags behind by a quarter period. Just as with direct current, the total voltage V in a series circuit is at any time the sum of the voltages VR and VC. This total voltage is neither in phase with I and VR nor with VC. Okay, how does that look within our phasor picture? We have one phasor for the voltage VR at some arbitrary angle at time 0. Since the voltage VC lags behind by a quarter period, its phasor is turned back by a quarter turn, that is 90 degrees. The amplitude of VC relative to VR depends on resistance R and capacitance C, but also on the frequency. Let's just assume that we chose a combination where VC head is 3/4 of VR head. Since both voltages have the same period, their corresponding arrows rotate at the same speed. The orientations of the arrows depend on time, but the relative position remains fixed. As they rotate, they generate the sinusoids for the two partial voltages. We can see how the sinusoid for VC trails the one for VR by a quarter period. To get the total voltage V, we have to add the voltage VC to VR. If we do this at every instant, we get a periodic curve for our total voltage with the same period as VR and VC. It certainly does look like a sinusoid, but is it? Yes, because we can find some phasor which generates our total voltage cycle after cycle. So how does this phasor V relate to the phasors for VR and VC? Interestingly, we can get the phasor V by parallel shifting the phasor VC to the head of phasor VR, or vice versa. Our phasor V is then the diagonal of a parallelogram of phasors VR and VC. Since this geometric operation is related to the addition of voltages, we can interpret it as a kind of addition of arrows. So far, we have only looked at the voltages. But what about the current I and its relation to the total voltage V? The current is in phase with the voltage VR across the resistor, so its phasor has the same direction as that of VR. However, the lengths may be different because the scales for currents and voltages may differ. As before, this current phasor generates the sinusoid for the current. But how does the current relate to the voltage? Voltage is a property of the electric field that drives the current. The relationship between voltage and current can be simple or complicated depending on the electrical component. For resistors in a DC circuit, Ohm's law applies. Voltage V equals resistance R times current I. This converts the current value to the voltage value and changes the unit. But what do we do in the AC case? To convert the phasor I to the phasor V, we need to change its length and unit and also rotate it. This turns the current sinusoid into the voltage sinusoid. Let's look at this in detail. Our voltage phasor V consists of the amplitude V head and the phase phi V, measured from the horizontal axis. But how does it relate to the phasor I? Well, the amplitude V head is certainly equal to V head divided by I head times I head. Similarly, the phase phi V equals phi V minus phi I plus phi I, where phi I is the phase of the current phasor. Now comes a leap of faith. We can write this as a product of two arrows if we accept that the multiplication of arrows multiplies their lengths and adds their phases. This gives us the required change in length plus the rotation. The first factor has a length of voltage amplitude over current amplitude. This is a kind of resistance which is usually denoted by Z instead of R. This Z multiplies the length of I to get the length of V. The phase difference phi V minus phi I is phi Z and is always measured from the current phasor to the voltage phasor. In our case, phi I is greater than phi V and thus phi z is negative, which means a clockwise rotation. This phase difference tells us how far we have to turn the current phasor to make it point in the direction of the voltage phasor. This kind of resistance is called impedance, and we can draw it as an arrow in our coordinate system after choosing a suitable scale. The second factor is simply our current phasor I. So we finally get that the voltage phasor equals impedance times current phasor. This is Ohm's law in the AC case, and it depends crucially on our multiplication of arrows, the multiplication of the lengths and the addition of their phases. While the current and voltage phasors rotate with angular speed omega, impedance is time independent. No matter at what time we divide the amplitudes of voltage and current and subtract their phases, the result is always the same impedance Z. Therefore, the phase differences are physically important, while the absolute phases are less so. Now, where does all that leave us? If we disregard the electrical cladding, there are two geometric operations with any two arrows in the plane starting from the origin. The first operation starts with two arrows A and B and proceeds like this. We parallel shift arrow B to the head of A, or we parallel shift arrow A to the head of B. Both shifted arrowheads meet in the same point because we have constructed a parallelogram. The result of this operation is an arrow running diagonally from the origin to the shifted heads. We call it the sum of A and B and the operation addition. To call this geometric operation addition, we should have similarities to the addition of numbers, and indeed we do. By way of constructing the parallelogram, A plus B equals B plus A, so operation is commutative. Let's say we have three arrows, A, B and C, and want to add all three together. One way to do this would be to start by adding B to A, giving us A plus B. And if we then add C, we get A plus B plus C. A different way would be to add C to B first, giving us B plus C. If we add this sum to A, it looks like we get the same result as before, but do we? By construction of B plus C, we have a closed triangle. Since all arrows with the same color are parallel to each other and have the same length, we can find a copy of our triangle shifted to the head of A. Therefore, both variants give the same result, which means our construction is also associative. Now there's a special arrow with length 0, the zero arrow. We can draw it as a dot. If we take any arrow A and add our zero arrow, the result is simply A. This zero arrow acts as a neutral element for our operation. Finally, if we want to solve an equation like Z plus A equals B, we have to undo the addition of A to Z. So we have to find an arrow which added to A gives the zero arrow. Obviously, an arrow of the same length but opposite direction does this trick. This arrow is called additive inverse or opposite arrow and is denoted as minus A. Adding minus A on both sides of our equation yields Z plus the zero arrow, which is just Z on the left side, and B plus minus A on the right side. The latter can be simplified to B minus A, which is called subtraction. In summary, our geometric operation with the parallelogram rule obeys the same rules as the addition of numbers. In fact, the parallelogram rule for combining arrows yields a meaningful addition in any number of dimensions, even infinitely many. What about our second operation? It starts again with two arrows A and B, where A has the angle alpha and B the angle beta with the horizontal axis. We start with A and multiply its length by the length of B. Then we turn this intermediate arrow by angle beta. We call the result the product of the arrows A and B, where the lengths have been multiplied and the angle is added. These are two operations combined into one, scaling and rotation. We already know the scaling part from the real numbers and, as we will see, also the rotation. The two sub-operations are independent of each other, so it doesn't matter whether we scale first and then rotate or vice versa. So far, we have only animated the multiplication, but can we construct it like addition? Yes, using a method published by René Descartes. So we could call it multiplication à la Descartes. We first draw a ray L1 from the origin in the direction of A and another one L2 in the direction of B. Next, we draw a unit circle that is a circle with a radius of 1 unit of length. Now we can draw a line L3 through the head of A and the intersection point of L2 with the unit circle. We can then parallel shift a copy of L3 to the head of B, giving us line L4. Finally, we can draw an arrow C to the intersection point of L1 and L4. What can we say about the length of C? Well, by construction, lines L3 and L4 are parallel. We thus have two similar triangles, a large one here and a smaller one here. The intercept theorem implies that the length of C to the length of A is equal to the length of B to 1, the radius of the unit circle. Hence, the length of C equals the length of A times the length of B. So we have an arrow of the correct length, now we need the correct angle. We are already in the direction of A, so we have to add the angle of B. We can do this the following way. First, we take the chord to B on the unit circle in the compass. Second, we plot it away from A on the unit circle. This construction adds the angles of A and B. Finally, we have to turn our intermediate result C in this direction to get our product A times B. But what if we start our construction with B instead of A? The ray L1 is then in the direction of B and the ray L2 is in the direction of A. The line L3 now runs through the head of B and the intersection point of L2 with the unit circle. We again parallel shift a copy of L3 to the head of A to get line L4, and we draw an arrow C from the origin to the intersection point of ray L1 with line L4. By construction, we have two new similar triangles, a large one here and a small one here. The intercept theorem now implies that the length of C to the length of B equals the length of A to 1. Hence the length of C is again the length of A times the length of B. Since C now points in the direction of B, we have to add the angle of A. We take the chord to A on the unit circle in the compass and add it to B. Finally, we turn our arrow C in this direction, which gives exactly the same result as before. Some final remarks. In the case where arrows A and B are parallel or antiparallel, we need to draw an oblique line to them and transfer the length of B to this line with the compass before we can start our construction. And if at least one arrow has an angle between 0 and 180 degrees, we can add this angle counterclockwise to the other using the chord as we've seen. If both angles are greater than 180 degrees, we have to do the addition clockwise. In any case, our construction gives a commutative multiplication of arrows. Let's say we have again three arrows, A, B and C, and want to multiply all three together. We could start with A and B, which gives us AB. Then we can multiply this result by C to get AB times C. We could also have started with B and C first, giving us BC. And if we multiply this with A, it looks like we get the same result. But do we? Well, we have two triangles, a brown one here and a teal one here. In the brown triangle, side B was multiplied by A to get the side AB. Similarly, in the teal triangle, side BC was multiplied by A to get the side A times BC. Hence the two triangles are similar to each other. On the other hand, since they are similar, the teal triangle is the brown triangle scaled and rotated by the factor C. This gives the sides BC and AB times C. Therefore, AB times C must equal A times BC, and our construction is also associative. There is also a special arrow for multiplication, but it is different from the one for addition. It is the unit arrow with length 1 and angle 0. In order to multiply any arrow A by this unit arrow, we need again the rays L1 and L2 in the directions of the factors. Then we draw the unit circle and line L3 through the head of A and the intersection point of L2 with the unit circle. This intersection point happens to be on the head of the unit arrow. If we then parallel shift L3 to the head of the unit arrow, we don't have to do anything because we are already there. So our product has the same length as A. Now we have to add the angle of the unit arrow to the angle of A using a compass, which changes nothing. Thus our product has the length of A and also the angle of A, which means it is A. Therefore, our unit arrow is the neutral element of multiplication. As with addition, we'd like to solve equations like z times A equals B. To do this, we have to undo the multiplication of z by A. So we have to find some arrow which multiplied with A gives the unit arrow. How can we construct this inverse arrow? We have again a ray L1 in the direction of A. And we would need a ray L2 in the direction of our inverse element, which we don't have yet. But we know that if we add the angle of our inverse element to the angle of A, we must get the angle of the unit arrow, which is 0. Using the unit circle, we take the chord from A to the horizontal axis in the compass. Then we plot it away clockwise from the unit arrow on the unit circle. If the arrow A points downward, we have to do it counterclockwise. This gives us the direction of ray L2. Since the centers of both circles lie on the horizontal axis, we have effectively reflected ray L1 on this axis. Now we need the length of the inverse element. To multiply A with its inverse element, we first draw the line L3 through the head of A and the intersection of L2 with the unit circle. We would now parallel shift a copy of L3 to the head of the inverse element, which we still don't have. But the result of this parallel shift would be an intermediate arrow in the direction of A with the same length as our product. And this length must be 1, because our product is supposed to be the unit arrow. So if we parallel shift a copy of L3 to the intersection point of L1 with the unit circle, we get line L4. The head of the inverse element of A is then at the intersection point of L2 and L4. This multiplicative inverse element, or reciprocal, is usually written as A to the minus 1. Its length is 1 divided by the length of A, and its angle is minus the angle of A. Coming back to our equation, we can now multiply both sides by A to the minus 1. This gives Z times the unit arrow, which is just Z on the left side, and B times A to the minus 1 on the right side. The latter can be simplified to B divided by A, which is called division. We can construct the inverse element for almost any arrow. However, if the length of A decreases to 0, line L3 lies atop ray L2 and line L4 is parallel to them but doesn't intersect L2. This means we have an inverse element to every arrow unequal to the 0 arrow. As with real numbers, we cannot divide by 0. So our weird rotational scaling gives us a multiplication that follows the same arithmetic rules as the multiplication of real numbers. There's only one property left we still have to look into. So far, we have two operations that seem to have nothing to do with each other, but we'll now show that they are connected. We start again with three arrows A, B and C. First, we add B and C and get the diagonal of a parallelogram with sides B and C. If we multiply the sum by A, we get A times B plus C. But what if we first multiply A times B and A times C? Then we can add them to a new parallelogram, and it seems that their sum is the same result as before. To show that this is indeed the case, we argue similarly as for associativity. Instead of triangles, we have two parallelograms, a brown one here and a teal one here. The sides of the teal parallelogram are the sides of the brown parallelogram, scaled and rotated by the same factor A. This means that the teal parallelogram itself is just a scaled and rotated copy of the brown parallelogram, and this must also be true for its diagonal. So on the one hand, it is the scaled and rotated diagonal A times B plus C. On the other hand, it is the diagonal of the teal parallelogram, which means A times B plus A times C. So we do get the same result both ways, and our strange multiplication does distribute over our addition. Therefore, our geometric constructions satisfy the distributive law. So we have the set of all arrows in the plane starting from the origin, and we have two constructions with nice properties operating on this set. Namely, the parallelogram rule, which is similar to the addition of real numbers, and the rotational scaling, which is similar to the multiplication of real numbers. Under these two operations, our arrows behave like a kind of numbers, therefore it is appropriate to call them numbers, the complex numbers. Apart from behaving similarly, is there a more direct connection between real and complex numbers? Well, there is something interesting with our two constructions. If we restrict ourselves to arrows along the horizontal axis, that is to angles of 0 or 180 degrees, our constructions will again yield arrows along that axis. In the case of addition, the reason for this is that our parallelogram is squeezed down to a line segment on the horizontal axis. So if we add, for example, arrows of lengths 2 and 3, both with angle 0, we get an arrow of length 5 and again angle 0. That sounds very much like 2 plus 3 equals 5. Let's try another example. If we draw our arrow of length 3 and angle 0 in the opposite direction, we get its additive inverse arrow minus the arrow of length 3 and angle 0. But we could also have rotated our original arrow by 180 degrees to get its inverse. In the plane, inversion and rotation by 180 degrees around the origin are the same. Anyway, now we add our arrow of length 2 and angle 0. The result is an arrow of length 1 and angle 180 degrees, which, by the same rotation argument, is minus the unit arrow. All that reminds us of minus 3 plus 2 equals minus 1. So it seems that we can represent real numbers as arrows along the horizontal axis. The arrows representing positive numbers have angle 0 pointing to the right, while the arrows for negative numbers have angles of 180 degrees pointing to the left. For example, the arrow of length 4.75 and angle 0 represents the real number 4.75, and the arrow of length pi and angle 180 degrees represents the real number minus pi. Similarly, the 0 arrow represents the number 0 and the unit arrow represents the number 1. Let's see how this works for multiplication. If we multiply the arrows of lengths 2 and 3, both with angle 0, we get an arrow with length 6 and angle 0. This is consistent with 2 times 3 equals 6. What about the multiplication of negative numbers, say minus 2 times 3? We have to scale the length of the arrow for the number 3 by 2 and rotate it by 180 degrees. This gives us an arrow of length 6 and angle 180 degrees, representing the number minus 6, which gives the expected minus 2 times 3 equals minus 6. Last but not least, let's look at the multiplication of two negative numbers, say minus 2 and minus 3. We have again to double the length of the arrow representing minus 3 and rotate it by 180 degrees. This gives an arrow of length 6 and angle 360 degrees. Since 360 degrees give the same direction as 0 degrees, we will consider them the same. Thus, our construction also gives us minus 2 times minus 3 equals 6. So we have already used the addition of angles as part of multiplication since the day we learned about multiplying negative numbers. We didn't really see it because we were limited to angles of 0 and 180 degrees. Also, instead of arrows, we used a different representation of numbers as strings of digits. And instead of constructing our results, we applied some algorithms that work with these strings of digits. All of this means that the real numbers are embedded in the complex numbers and that the complex numbers are a natural extension of the real numbers. So far, we have not labeled our axes. It would be perfectly okay to call them x and y axes, but that's not what is usually used. Since the arrows representing real numbers live on the horizontal axis, this axis is called the real axis. But we are no longer limited to a one-dimensional axis. We can roam freely in a two-dimensional plane. In particular, we can move laterally away from the real axis. That's why Gauss wanted to call the vertical axis the lateral axis. But Descartes, of all people, coined the term imaginary to mock the use of these numbers. Unfortunately, Descartes' term is still used today and the vertical axis is called the imaginary axis. Yet it is still a perfectly normal axis in a real plane. Now, all arrows on the real axis are real multiples of the unit arrow with length 1 and angle 0. This unit arrow, representing the number 1, is the real unit. In order to get away from the real axis, we need a similar unit along the imaginary axis. The usual choice is an arrow of length 1 and angle 90 degrees. All other arrows on the imaginary axis are real multiples of this arrow, so it is called the imaginary unit. In mathematics, this imaginary unit is denoted by I. In electrical engineering, however, I already stands for the current, so people use J instead, as I will do in this video. Using minus J as imaginary unit instead of J would also have been a possibility, just as minus 1 would have been instead of 1. The imaginary unit has a very interesting property. If we multiply J by itself, that is square it, we have to scale its length by 1 and add another 90 degrees to its angle of 90 degrees. This gives us an arrow of length 1 and angle 180 degrees, which represents the real number minus 1. So the imaginary unit J squared equals minus 1, a fact that can be very useful to solve algebraic equations. So far, we have added and multiplied arrows using constructions. Now it's time to find an algebraic representation of complex numbers. Let's consider an arrow A in the plane. We can decompose it into the sum of two arrows along the real and imaginary axes. The first arrow is a real number AR times the real unit 1. The second is a real number AI times the imaginary unit J. So we can write A as the sum AR times 1 plus AI times J, or more briefly, AR plus AI times J. This is the Cartesian or rectangular representation. In our example, A equals minus 3 plus 2J. We call AR the real part and AI the imaginary part of A. The length of our arrow is the absolute value or the modulus of the complex number A. We can calculate it using the Pythagorean theorem and get the square root of AR squared plus AI squared. The great advantage of the Cartesian representation is that we can now do calculations in a similar way as with terms in parentheses. Say, we want to add the complex numbers A and B, each being the sum of a real and an imaginary component. We parallel shift B to the head of A, and the components of B are shifted along with it. This gives our sum A plus B. But instead of adding our two arrows A and B, we could as well add their four components along the real and imaginary axes. Using our addition and distributive properties, we can rearrange their order and factor out the imaginary unit J. In total, the real part of the sum is the sum of the real parts, and the imaginary part of the sum is the sum of the imaginary parts. This is exactly like adding terms in parentheses and treating the imaginary unit J as some variable. In our example, A is 3 plus 1J and B is minus 1 minus 2J. The sum of the real parts is thus 3 minus 1, and that of the imaginary parts 1 minus 2, which finally gives the sum 2 minus J. Let's look again at some arrow A and its components AR and AI times J. The additive inverse minus A is an arrow of the same length as A, but opposite direction. But this must also be true for its real and imaginary components. So minus A is just minus AR minus AI times J. Again, the same as simplifying terms in parentheses. What about multiplying A and B in Cartesian form? If we multiply out, we get ARBR plus ARBI times J plus AIBR times J plus AIBI times J squared. Remembering that J squared equals minus 1, we get the real part ARBR minus AIBI and the imaginary part ARBI plus AIBR. This is a very strange combination of the real and imaginary parts of A and B, and it makes no sense to memorize it because we can always reproduce it by multiplying out and using J squared equals minus 1. But does this really multiply the lengths of A and B and adds their angles? To simplify, let's do only the first step and ignore the components of B. We get AR times B plus AI times J times B. Now the multiplication by J just turns an arrow forward by 90 degrees, and this is also true for its components. The turned arrow J times B has the imaginary component BR times J and the real component BI times J, which is BI times J squared. Since J squared is minus 1, this gives minus BI. Now we have to scale B by AR, which gives the real component ARBR and the imaginary component ARBI times J. Similarly, we have to scale J times B by AI, which gives the real component minus AIBI and the imaginary component AIBR times J. Finally, we have to add the scaled arrows. For the real component we do get ARBR minus AIBI, and for the imaginary component we get ARBI times J plus AIBR times J. But is this sum really our product A times B? Yes, because both legs of the big right triangle are the legs of the small right triangle scaled and rotated by the same factor B. And this must also be true for the hypotenuse. It never ceases to amaze me that this strange combination of real and imaginary parts multiplies lengths and adds angles of arrows. Algebraically, this is due to the choice of J squared being equal to minus 1, which could indeed have been a different choice. In our example, A equals 2 plus 1.5J and B equals minus 2 plus J. Multiplying out, we get minus 4 plus 2J minus 3J plus 1.5J squared. Using J squared equals minus 1, we finally get the product minus 5.5 minus j. The Cartesian representation makes this really easy. To finish, what about the multiplicative inverse or reciprocal of a complex number a? We've already seen that the reciprocal lies in the direction of a reflected on the real axis. If we reflect a on the real axis, we get the so-called complex conjugate of a, written as a star. All we have to do is change the sign of the imaginary part of a. Therefore, the length of a star is the same as the length of a. Now, our reciprocal must lie somewhere on the real in the direction of a star. Algebraically, this means that a to the minus 1 equals k times a star, where k is a positive real number. We've also seen that the length of a to the minus 1 must equal 1 divided by the length of a. This implies that k times the length of a star must equal 1 divided by the length of a. But since the length of a star equals the length of a, our factor k must be 1 divided by the length of a squared, or 1 divided by ar squared plus ai squared. Thus, the reciprocal a to the minus 1 is given by the complex conjugate of a divided by the squared modulus of a. So the real part is ar divided by ar squared plus ai squared, and the imaginary part is minus ai also divided by ar squared plus ai squared. This concludes our introduction to the basic arithmetic of complex numbers. Although their name works to the detriment, complex numbers are one of the most beautiful subjects in mathematics. They make working with sinusoids and sums of sinusoids so much easier and open the gates to Fourier analysis. Also, important geometric operations such as translation, rotation or scaling can easily be done as complex additions or multiplications. And quantum mechanics without complex numbers is just impossible. Not to forget electrical engineering, where AC voltages and currents got us started with complex phasors. However, instead of our nice complex amplitudes, electrical engineers rather use complex root mean square or RMS values. But for pure sinusoids, the RMS value is just the amplitude divided by the square root of 2.